So we've spent all that time on all these other things over our course of boot camp. Now we're going to talk about pretty much like all of second half of pre-calculus, trigonometry, and all our fun radian goodness is what we're going to be covering today. So this is kind of like the second half of pre-calc, what we're talking about today. So a couple reminders. The idea of a radian is that here's our radius, and if you have an angle that's 1 radian, this arc is the same as this piece. I said something similar to this in pre-calc, but this is another way to talk about it, that the radius and this arc, if those two are the same thing, you've got a radian on the inside. Mostly you care about if you're translating back and forth between those two. We use 180 over pi and pi over 180. It's kind of the simplest way that we can talk about it. You could also use 360 degrees and 2 pi or any other combination of radian measure and degree measure, but it's up to you which one to use. Standard position, we've got our initial side. We're always starting on the positive part of our x-axis, and then we move counterclockwise around our circle for positive angles, and then clockwise for negative angles. And then you've got some stuff down here about like you've got between 0 and 90, 90, 180, blah, blah, blah. Quadrants 1, 2, 3, and 4. Again, moving counterclockwise around our radian circle. So if we have an angle of 5 pi over 8 and a radius of 2 pi, we want to know what that arc length is. It's really easy. It's just this times this. Button, where's the button? This times this equals that. It's really easy in radian mode. In degree mode, there's a whole bunch of other calculations and garbage you have to do, but in radian mode, you just multiply those two together. So you get 10 pi over 8, which you would obviously simplify because we want to give a nice simplified answer, 5 pi over 4. Woot! Sweet. Certain ratios in our triangles that we want to remember is 45, 45, 90 and 30, 60, 90s. The 45, 45, 90 was the easier one because two of them matched. And then the other side is square root of 2 over 2. Then for 30, 60, 90, your smallest one is 1. So across from our 30-degree angle, our smallest one is just 1. And our biggest one is our hypotenuse, which turns out to be 2 because of a big proof garbage that we did way back when, but we're not going to worry about it anymore. We've also got square root of 3x. That's kind of our leftover one. I kind of remember that the square root of 3 and the 30 are kind of like right next to each other. Well, it's kind of bad to remember, but unfortunately, it's how I memorized it. But you've got x, 2x, and square root of 3. Comes from the Pythagorean theorem. Not that you care. So if we wanted to evaluate this thing, so we've got arc sine of 2x, and we want to figure out the sine of x, we're going to sketch this right triangle, and then we're going to try to figure out what all of this stuff turns out to be. So that arc sine. So arc sine was not something that we actually talked about. Well, we talked about it, but we didn't really necessarily write it. Arc sine is actually talking about sine -1. So inverse sine is what we usually called it instead of arc sine, 2x. Inverse sine of 2x, so that's telling us, okay, well, the inverse sine of whatever that is. So that's just going to be some angle. I'm going to pick this one just because I'm drawing the triangle, so I can put it wherever I want. So arc sine of 2x. So this is 2x, because sine is opposite over hypotenuse. And then we're just going to do the sine of that. So really, this inverse sine of 2x, or arc sine of 2x, that is just whatever this angle happens to be. I don't really know what that angle is. And frankly, I don't care. Because then it's just asking me, what's the sine of that angle? Well, I just kind of put it there. Sine is opposite over hypotenuse, so this is just 2x. There is an example where you need to do a little bit more with this, and that's kind of why I'm making this drawing. If we wanted to figure out the missing angle right over here, we would just use the Pythagorean theorem. There are problems where you do need to figure out that missing piece. So that's why I threw this in here. But also I wanted to talk about what arc sine was. A couple things other than arc sine, so that is undoing sine, there was also the reciprocal function. So the sine and cosecant were reciprocals of each other. They're upside down versions of each other. Cosine and secant were reciprocals of each other, just flipped upside down. Wait, am I doing this? Yeah, I'm doing this right. What is this? This isn't right. See how these are both Y? They're all YRs. Oh, Honegs. Oh, gosh. I just saw this page and I was just like, oh, whatever. So this is R over X, and then this is X over Y. Yuck. Um, so uh, cosine and secant, they're reciprocals of each other. Tangent and cotangent, they're reciprocals of each other. They're upside down versions. There's also this positivity chart. All students take calculus, all senators talk crap, whatever you used. In this quadrant, all three of our trig functions are positive. In this quadrant, sine is positive, but tangent and cosine are negative. Here, tangent is positive, but sine and cosine are negative. Here, cosine's the only thing's positive. So this is talking about who's positive in what quadrants. That was too far. Well, really, it was just one of just, if you wanted to do all these things, I do them in the PDF notes. They're just upside down versions. Very boring, not worth our time. There's this thing, the unit circle. I hate this thing. If you really wanted to use it as a reference, you could have it, but this should not live in your brain because it's just, for me, it's too much. If you can get that to live in your brain, great. But for me, I just cannot get this thing to live in my brain. What can live in my brain is the golden nugget. And look, I typed this one up so that it looks pretty for you. So the golden nugget is something that you should have living in your brain at all times. We wrote all this down. I did add a couple things. I added this little like reference angle chart, which I think is helpful, but all this other stuff should have been there already. We've got cosine, we've got sine, we've got tangent. This is how you calculate the other quadrants. Here we've got our positivity chart, important angles, how we created the unit circle, radius of 1, all that good stuff. So make sure that this golden nugget is still living in your brain because it still needs to be in there. We're going to use these a lot and just at random times. You'll never know when it's coming. It's just be always ready to do trig stuff. Our practice assignment actually goes back a couple sections because I've kind of been leaving it out, but you might have seen it in some of the other examples. There was sine and cosine showing up. Arcsecant, once again, that's doing undoing secant. So, can I have a pen, please? Thank you. So secant -1 of negative square root of 2 over 2. Square root of 2, I'm getting ahead of myself. Now, one question I probably asked you on the oral exam was, but I didn't say inverse, and I didn't use secant. Let secant equal negative square root of 2 over 2. Solve for theta between 0 and 2 pi. So here we're just trying to figure out what angle would have spit out square root of 2 over 2. I keep saying square root of 2 over 2. You can tell where I'm going with this because we didn't do secant, we did cosine. So we need to flip this thing over. So really it's asking about, hey, cosine of theta equals square root of 2 over 2, but negative, right? So I know which angle does that. It's pi over 4. And then there were two quadrants where cosine would spit out pi over 4. It was in the second and the third quadrant. That's where cosine is negative. So it could have been in the second quadrant, it would be 3 pi over 4. And in the fourth quadrant, it would be 5 pi over 4, not 4. 5 pi over 4. Now this one's doing arcsecant, and what that's trying to say is like, hey, we don't want to worry about the additional example. So all we're going to do is we're just going to take the smaller one. So 3 pi over 4 is what we're looking for this one. So yeah, it's like what we did on the oral exam. It's just got a little bit of extra steps to it. Here's another one we're going to solve. This one's a little bit closer to what we've done on the oral exam. I think I probably gave you this one almost verbatim, but I didn't do tangent on there, but we can still do tangent. So 2.5, I want to first check if that's one of the things on the unit circle. So 2.5, I can make it 5 over 2. 2.5, yeah, 5 over 2. 5 over 2, 5 halves. Now, you'll notice that that's a number that's bigger than 1, so it's a number that's gotten quite big. And remember, tangent, the way it works is it kind of shoots up and becomes really, really big. So that one's a little bit outside of the range of what I know. I don't know of 5 halves. That doesn't pop up on me. I know square root of 3 over 3, I know 1, and I know square root of 3. But 5 halves, I don't know that one. So I'm just going to use inverse tangent. And I'm going to do this one on my calculator. Let me pause quick while I get that. So tangent 5 halves, I want to just type that into my calculator. So second inverse tangent of 5 halves. Yeah. And I also, before I did that, actually, I checked it while I was paused, but I forgot I was going to check it with you all as well. Double check to make sure that you're on radian mode. So I pressed my mode button, and I want to make sure I'm on radian for this thing because it's talking about things in terms of radians right there. So inverse tangent is 1.190. But I do care about, for this one, it's giving me that hint of like, hey, I want to be between 0 and 2 pi. So I need the two quadrants where tangent is positive. I know tangent is quadrant in the first positive in the first quadrant, is quadrant in the first positive, and it's going to be positive in the third quadrant. In the first quadrant, we talked about, well, we didn't talk about, but it was on the thing. In the first quadrant, your reference angle, because that's what this thing is. It's my reference angle. It's not my answer. But in the first quadrant, reference angle is my answer. So in this one, it's 1.190. And in this bottom quadrant, we need to do pi plus my reference angle. So let's do that. So I go second pi plus my reference angle, which I just had, and 4.332. The next one I will do in the video notes because I just took a look at the time and I've been going a little long. But it does do one little thing since it's going from negative infinity to infinity. You need to add on that these things go for forever and ever and go on and on and on. So if this one had that, what I would do is I need to add that spins around the circle. So for that 1.190, I would add plus or minus 2 pi n. So that would let it spin one way around the circle and then the other way around the circle. You do the same thing with the other one, plus or minus 2 pi n. So round and round, round and round the other way. On the PDF notes, I'll actually work through some graphs of these so that you can just see how like the graphs work. They wobble, yeah, they're wobbly. Okay. We got to talk about period, domain, and range, and all that junk. Oh wait, mine's a little bit longer, so my time is actually probably not quite so bad as I think it is. So our period for this function, a quick reminder about the spots period shows up as 2 pi over whatever our b value is. In this case, our b value rather is always right next to the x. But it needs this extra bonus pair of parentheses around there. If it's not there, you need to add them. You can't just willy-nilly add them. We need to then divide out that 3 that we took out from that parentheses. Imagine if that 3 was distributed back in, turn right back into pi. In terms of our period, it doesn't really change. 2 pi over b, which is 2 pi over 3. So that's how long it's going to take for our graph to complete one of its loops. The domain of this function is how far what things work for it. Cosecant has certain spots where it's freaking out. We're going to take care of it. We're going to spot that on the graph. We also care about its range, where it's good. We'll spot that on the graph. I think making this graph is going to make our lives a lot easier. So let's do it. Let's graph this thing. I would like to actually do this one on Desmos. Give me a minute while I set that up. Okay, so I've got this all set up in Desmos. Now I did a little work just to make sure it looks nice. So here's our graph. Desmos does understand cosecant. Your graphing calculator doesn't have a button for it, so you just type 1 over sign instead of cosecant, and then you type all the stuff that goes inside of it. Now, quick reminder about how we graph these things. We did graph these in pre-calculus, but the way we graph them is we actually graph just regular sine. So we would graph sine using all these tricks. We would first take care of our period. That was the first thing we graphed. We went 1, 2, 3, 4, and we wrote our period, which was 2 pi over 3. Then we would need to move up 2 because we have this plus 2. So here's our start point. It needs to move pi to the left, so it kind of goes back this way. So here you can see it's kind of sliding to the backish. That's why it's going down first instead of up. So it's supposed to go up. So really this thing is starting back here as your first initial point, and then we would wobble from there. But I'm just keeping it positive just because it's easier to look at. And then we're changing how high and low it goes. It goes down 3 and it goes up 3 based on our amplitude right here of 3. Then, once we have done all that stuff, then we would say, okay, well, by all of that, and we need to say, okay, well, I want cosecant. And what cosecant does is it bounces off of the tops of sine. If we had secant, secant would bounce off the tops of cosine. Tangent is weird and crazy, and cotangent. So this is our actual graph of cosecant. It's all of these parabolas that are bouncing away from each other off of the tops of sine. So back to that thing we were talking about earlier about domain and range. So range is really easy. I'm going to take care of that first. We can see our range pretty simply. We're way down here. We go up to this point, which is at 1. And then it continues on up to 5. So our range, and then once it doesn't continue on. It's got a gap. So it starts down here, goes to -1, big old gap, get to 5, and we continue on. So for our range, not bracket, thank you. So we go from -infinity to -1, bracket, because we reach the top of those parabolas. Then we get a u, another bracket, start again at 5, and we go to infinity. Domain's a little bit worse. So domain is taking a look, I don't want that, I want this. Domain is looking at, it seems to be everything. Everything seems to be fine, but there were a bunch of gaps. Every place that sine touches the sinusoidal axis, cosecant freaks out because at this point, in a sense, sine becomes 0 and it's in the denominator. When you put a 0 in the denominator, everything freaks out. So whenever it's touching this 2 spot right here, cosecant is freaking out and it doesn't exist. So we have to skip all of those spots. Fortunately, they're pretty easy to spot. Take a look. There's one right here. There's another one here, another one here, another one here, and another one here. It's at all the pi over 3s. By the way, if you're interested in how I set it up like this, if you go over to graph settings, you can change the step. So I just typed in pi over 3. And you can even go here and you can type like what you want for your window. You can just type in like pi over 3. Makes really nice windows really quickly for you. Double check that you're in radian mode. Okay. So it's all the pi over 3s. So we just got to find a way to write that. So it's all real numbers. So here I'm gonna cheat. I'm gonna use the R. So just big ol' R. Except x cannot equal. We need all of the pi over 3s. So we need pi over 3. We need 2 pi over 3. We need 3 pi over 3. We need 4 pi over 3. We need 5 pi over 3. So we just need n pi over 3s. You can put plus or minus in front of that too. So that is our domain, and that is our range. And I've already drawn the graph. That was on the other doodad. There are two more problems that I'm going to do in the PDF notes that you can check out. So there's this one of secant. So I'm going to show you how you find that algebraically. I'll do another graph if you want to see another graph. And yeah, here I'm just going to talk a little bit more about this, but I think the video has been going quite for a while, so I'm just going to cut this off. So important things that I want you to get out of today. I don't really care about the graphs that much. What I do care about is you remembering your golden nugget. Make sure that you remember how to do these trig functions, how you can calculate these trig functions. Graphing is less of a big deal, and that's especially why I'm just kind of hand waving my way through it. It's more just forcing you to think more about the trig functions. But if you know how to do your oral exam, that is going to be the big thing that's going to be helping you out, I feel, for calculus. So make sure that you really have this golden nugget living in your head. All right. So thanks. Have a good day.